Hello everyone, welcome to this very interesting tutorial. This tutorial is presented by Rakesh Herurkar. You should check out his LinkedIn profile. I have given the link in the description. So we'll use Vellum Solver, Vellum Fluids to create this droplets kind of getting attracted towards the center and forming a bigger puddle. Let's dive in. Create a geometry node and let's call it droplet. I'm going to put down a grid like 5 by 5 and scatter some points on it. I'm going to scatter like 25 points and remove this relax iteration. We are going to do it uh, using the relax node, and then I'm going to create p scale attribute in it. So attribute adjust float, and we'll create a random value between 0.07 and 1. Let's create a sphere. Make sure it is a polygon, and I'm going to compress the radius in y axis to 0. And put down a match size just to make sure the droplets are staying on the ground. So currently it is not. Change the justify y to minimum, and then let's copy to these points. They are intersecting, so let's put down a relax node, point relax, and check this relax in 3D space. So based on this point radius, it is going to relax. Just a value of 1 should be enough. Okay. Let's put on a rest node and store the rest value. So the rest value is just the position here. Normally it is going to be the initial position, but this is a static geometry, so just the position. And then we will convert it into vellum fluids. So put down a vellum configure fluid node. The particle size 0.03, and in the physical attributes, let the density be 1000, but increase the viscosity to 100. So we want a bit more viscous fluid, not very watery actually, a bit thick, and that is it. But one thing is, like, we are going to lose these attributes. The rest attribute is not going to be there. Let me change to technical. So the rest is missing. Also, one thing I forgot is put down an attribute adjust node and create a mask attribute. So this mask attribute is what we will use to control the points that are like getting attracted towards the center. Basically, this will be the value that uh, that pulls the points towards the center. Okay, so let's create a random value for this and change this to mask. Okay, and it will be a random value, but the maximum value will be only 0.5. Okay. Okay, so currently we can see that the value is like kind of a ramp, but initially we will make all the values to 0 just to show you like how it works. I'm going to make this value to 0, and later I'm going to come and do something here. So here we are not getting the mask value also. So let's transfer the attributes. Okay. So now we have the mask value. It is all 0 right now. And then the p scale. The p scale doesn't seem right. It's okay. We don't need the p scale. But we have the rest, I think. Yeah, we do have the rest. And then we'll put on a Vellum solver. And connect the constraints. And we are going to add ground. First thing first, we'll add a ground. Or else the droplets are going to fall. And the substep value of 3, but currently we'll work with 1. Later we'll come and change it to 3. Okay. So already we have some vellum fluids that is already viscous, and we are we are ready to implement the pulling logic. So let's dive in. We can use this pop axis force and connect it to the force. Increase the radius. You see this red marker, this is the radius. We need a bit higher, like 3.2 or even 4, I think. Yeah, something like this. So only the points within this radius are going to be affected. And then let's turn off the orbit speed. So if you don't turn off the orbit speed, they are going to rotate. Okay, let's just make it 0. But instead we are going to have suction speed. Okay, so we'll start with the value of 1 and it gets attracted. So he has used a value of 5. Yeah, it may look very fast, but he is eventually multiplying this value with the mask value. So now all the points are like getting attracted towards each other, but we need to do it one by one. So we are going to animate this mask value first and multiply this mask value with the suction speed. So currently if we multiply this mask with the suction speed, everything are going to be 0. Okay, so let's do that first. Float mask is equal to, so basically first we need to bring in that value. By default vellum doesn't bring in the values, so change this input 1 value to first context geometry. So basically whatever we are giving here, we are going to get the values into the expression. Okay, we can access it like this: point 0 mask and pt norm. Based on pt norm they are going to match them. So now we can multiply this with the suction speed. Let's see what parameter this suction speed has. It is suction speed without any space. So suction speed into equals mask. So currently the suction speed will be 0 for every point, and they are not going to be pulled in towards the center. And now we can start animating this suction speed to a higher value for some points, and they will be sucked towards the center. That is the concept. So let's animate this value, but we need to create a higher value here. So something like this will start like frame 30 maybe, and so this one, let's key the position, and this also let's key the position, and maybe after like 200 frames, let me put it in manual. You can animate them towards like half. So what this means is half of the points are going to have a value of 0, but randomly some half, almost like half of the points are going to have a value of 0.5. So we will keyframe, and this also, let's make sure that there is a keyframe. Yeah. So basically it should animate like this. I'm going to visualize here and change it to automatic. If you see the mask value, we can see that they are going to, some points are going to have a value of, okay, initially they have a value of 0.5. So the initial keyframe will make this value to 1. So they are at the dead end, and we'll make sure that there are no mask value higher than 0. Okay, and now when we move forward, you can see some of the points are getting a mask value of 0.5, and it keeps on increasing, and a lot of points are going to have a mask value of 0.5. Now let's dive into the Vellum solver to see what is happening. So if what we did is correct, when the frames progress, like more and more points are going to have the suction in them. Okay, they are going to have the suction, and they're going to be pulled towards the center. Yeah, you can see some points are starting to get the mask value higher than 0, and they are getting pulled towards the center. And this is going to happen one by one. Nice. So this is exactly what we wanted, and we have got it. So for the fluids that are like flowing, that are being sucked in towards the center, we can add a bit of pop force. Okay, pop force, so that it gets a bit more interesting. The amplitude value of 5, and we'll do the exact same thing that we did here. We are going to multiply this amplitude value by the mask value, so that it is applied only to the points that are active, that are being sucked towards the center. Okay, let's copy this one here. So we are bringing in the mask value. Okay, don't forget it to change it to first context geometry here also, and then we'll see what is the parameter for amplitude. It is AMP. So we are just going to multiply it with mask. So this just makes the particles a bit more interesting. There is not going to be any like a huge change or anything. Okay, so now we can cache the fluids out. Put on file cache node. I'll call it fluid PTS, and I'm going to disable this for a second, and put down VDB from particles. Let's build the VDB mesh. Voxel size of 0.01, and the particle radius scale 3, and this minimum radius scale he has reduced it to 0. We have a basic shape, but we can smooth it out. So VDB smooth SDF, and we'll use this Gaussian value, the Gaussian operation, and we can increase the iteration to 8 for like a more refined fluid. Yeah, this is actually looking very good already. Since we don't have like much jitter in the simulation, it is the fluid mesh also should look very good. And then let's convert it into a polygon. Convert VDB and to polygon. So I'm going to cache this. I have cached out the droplets. I have cached out the points as well as the mesh, or else it is going to take some time to convert into VDP and then to polygons. So I have just cached out the mesh, but this mesh will not have these attributes like velocity. So let's get it transferred from the point. Let's transfer only the velocity. That should be enough. And if you see the final output, there are some coloring going on based on like if they are coming towards the center or not. So that coloring we can do using velocity. Put down a warp node, attribute warp, and so based on the velocity we are going to create a ramp of colors. For that we need to have like a float value that is between 0 and 1. So let's find out the length of this velocity, and let's bind it to some temporary attribute. Bind export. We'll call it test. And if you visualize this test attribute here, it's not going to be between just 0 and 1. It might be higher or it might be lower based on the magnitude of the velocity. Okay, so if the magnitude is like very high, the length of the vector is also going to be very high. Now for example, let's go to a frame where there is movement. Yeah, now the higher values, you see, it's greater than 1. And even further you go, the higher value will be like even more higher. So let's fit it between 0 and 1. Okay, fit range. This is going to be the value that we are going to fit. And so this value, this 0 to 1 value, we are going to give it into a ramp parameter. So ramp parameter, and we'll export this to color. And this RAM parameter we can give multiple colors, but one thing is we are going to promote this source minimum and source maximum. Okay, because we don't know the minimum and maximum value of the velocity, so we are going to manually adjust this to adjust the final output, the color. So let's promote this, middle click and promote parameter. And we are going to adjust this to adjust the color that we are giving here. So let's start coloring, like give a gradient to it. Maybe first we'll give like a purple color. So we can give multiple colors. So basically when the fluid is at different stage in the velocity, it will have different colors applied to it. We'll have some bluish, and some green, and yellow. So the final color will give yellow. So now when the fluid moves based on the stage, or based on how much velocity it has, it will acquire different color. Okay, and now this color ramp we can adjust by adjusting the minimum and maximum value for the fit. like how much we want. Yeah, so we can have it a bit sharper or like however you want. I'm just going to have something like this. So he has used a value of 1.5 and 0.13. So this should have some smooth transition, like the not very sharp. So let's blur it out the color a bit more. With an iteration 57. So we have some smooth transition in between the colors. Now let's create some droplets and we'll apply the same kind of color values to the droplets also. From the fluid points, we are going to select a particular percentage of points and copy some spheres to it. Put down a delete node. And we are going to delete randomly. We are going to delete like 99.5 percentage. Choose points here because we only have points, and based on the seed we are going to delete. Let's enable this delete by pattern. Yeah, so now we have only 5%, sorry, 0.5 percentage of the points. We can reduce the percentage to have more bubbles, but this should be fine. Okay, now we need to delete the existing point scale, like the p scale, and we will give our own p scale. Attribute delete, and let's actually delete everything except the velocity. So that is all we need. Now let's put down an attribute adjust node and create a new p scale. Let's first copy the spheres, copy to points, and some polygon spheres. Okay. So now we will randomly change the p scale. This is like too much. 0.01 to 0.1. Yeah, so something of this size. And let's again reduce this ramp a bit to have more smaller pieces. Yeah, so actually that is all. These are the bubbles that will travel along with the fluid, and we can actually copy the exact same thing over here to have the exact same color, kind of color scheme. So when the fluid moves, they should have some colors. Let's merge these two. And this we can render. Yeah, so that is all. So if you like the tutorial, please give a like and subscribe to my channel. I'll be back with more tutorials. Thank you.